What? Yeah, okay. Ah, you can tell the mic's on when you hear the feedback. Welcome to the 10th annual Christmas tree lecture. I just decided to start because 10 seconds had gone by and nobody coming through the door, but now all of a sudden more people are coming through the door. Well, that's okay. I'll just talk about silly things at the beginning. This is today we have co-sponsors. Not only is Computer Musings, but it's also sponsored by Stanford's Computer Forum Emeritus Lecture Series. So we're killing two birds with one stone. Actually 3 or 4 birds with one stone, because I'm also celebrating today the 35th anniversary of the Art of Computer Programming, which started to come out in 1968, and the 30th anniversary of Volume 3, which was the last one I got finished, which came out in 1973. So anyway, so in the Christmas spirit, I decided to bring a couple of spare copies of Volumes 1, 2, and 3, and those will go to the people who asked the best 3 questions. Today. So, but not just random questions, But anyway, I don't mind people asking questions. This is they said this is an annual Christmas tree lecture. It's something we started a while ago, and the idea is that every year about this time I've been talking about the most cool thing I learned about trees during the year. And so today I'm going to be talking about something that I learned in July and played around with a little bit at the beginning of August. It goes back really to things that I learned as an undergraduate in my circuits lab, the basic idea of spanning trees. And in fact, the first, one of the very first, if not the first, appearance of trees in the mathematical literature was the famous paper by Kirchhoff, I think 1840s, where he based a lot of theory about circuits on the idea of spanning trees. And people, electrical engineers have had to learn Kirchhoff's law ever since. So I guess I start out by telling you, this is the first time, though, since I have so many sponsors, the first time I've ever had a lecture with 3 different posters announcing it. Anyway, there'll be lots of souvenirs at the end. Okay. Spanning tree is this. We start with a graph, and a graph. I think you have to know what a graph is, but it's a bunch of points called vertices and a bunch of connections between those called edges or arcs. And in the announcement of today's lecture, I have this one example graph here with 6 vertices, and I might as well make those red, since actually it's orange there. So, and I connected them up very simply with making it into triangles. And then, but now in order to have a spanning tree, you have to have a subset of those edges. Have to have a subset of the edges that connects up all the points. So if I got 6 points, I'm going to need to choose 5 edges in order to connect them all up. And one way to do that, of course, is well, I got to connect this to one of the 2, so I can go there. Well, I could also actually connect it to that one, and then from there I could connect, say, to there, and maybe over here, and then to get this guy, I come either way. So let's say I went there. So that's a spanning tree. And all the spanning trees on the graph were important when Kirchhoff wanted to study electrical circuits that were hooked together in this way. Now, on this poster that announced the lecture, it turns out that you've seen many different spanning trees of this same 6-point graph. In fact, well, this one ought to appear somewhere. It sort of wraps around there. So where do I find that one? I hope it's on here.
What's the file? The bottom right.
What?
One row up.
Here it is. Good. Okay, we got it. So it turns out there's 54 spanning trees of this graph, and and that's not a triangular number, so I added a star at the top, and so we got. But they all appear here. But there's more to it than that, because if you look, there's a little thread connecting these guys, going like this, and each one, if you go from one spanning tree to the next, it's as close as possible to the previous one, in the sense that only one of the links has changed. So in order to get from here to here, I deleted, I deleted this guy and added the one at the bottom. To go from here to here, I deleted one more and added another one. And so all 54 are connected by this thread in this way. So okay, I had this on my computer a month ago, and my wife walked in and said, "Hey, let's use this on our Christmas card this year." So there we are. Now I put on the web a bunch of computer programs so that you can play with the ideas that I'm going to be discussing today. So I'm going to talk about a couple of algorithms that are nice ways, I think beautiful ways, to go through and find all the spanning trees, and also in this way that there's just a small change from one to the other. Because if you ever have a problem where you want to look at all spanning trees, usually you can save time if you whatever you're doing on the whole set of spanning trees, it probably doesn't have to change much between one and the other if only one of the edges of the spanning trees is changing at a time. So I've got these methods I'm going to explain, and also the computer programs are on the web if you just go to my home page. I'm very lucky that on most days this year I have a three-letter Google. You just go to Google and say DON and you get my homepage. So I don't have to tell anybody. So I don't have to tell anybody my URL now. And then you click under downloadable programs, and you find programs about spanning trees that I'm talking about. And so if you want to play with any of this stuff, it's going to be easy to do. And let me show you first one of the programs. Oh, okay, here I put it here. So it's called SP-span. So if I type SP-span, then you get a usage message that says what you should do is I'm getting ahead of my story. You're supposed to give a formula, and then you have some other parameters. So let me talk first. Let me talk about special kind of graphs for which the algorithm is particularly pretty, and that is called series parallel network. In fact, I guess black shows up better, although green is a better Christmas color. So series parallel networks, and that's what SP stands for. And again, it's something I had to learn when I was a sophomore. So the idea of a series parallel network is very simple. It's a way to connect a source to a source to a terminal to a destination terminal, or just let's say two terminals, U and V. And one of the simple series parallel network is just the one that connects U to V. It has only one edge in it, so there's a series parallel network. Or if you have several series parallel networks, say somehow between U1 and V1, U2 and V2, UK and VK, then you can connect them in series, and so that means that you say V1 and U2 are the same vertex, V2 and U3, and you join them up like this. So the series connection is U1 V1. Let's say V2 this is equals U2, and V2 equals U3, and so on, and finally we get to the end at VK. And here we had a UK and a VK minus 1. So now these aren't, but between U1 and V1, it isn't just an edge. It's any series parallel network between U1 and V1. So it could be an edge, but it also could be a super edge a super edge being anything I've already defined as a series parallel network. And the other thing, of course, is the parallel connection, where we say that U1 equal U2, all the U's are equal, and all the V's are equal, and we just hook them all up like that. So this guy I showed here is actually a special case of a series parallel network in many ways, but let's see if we can find at least one of them.
You disallow the empty set of edges.
What?
You disallow the empty set of edges.
The empty set of edges is not a series parallel network. Yeah. Sorry, this is it though. Much better. So you have a grammar that in fact you can reduce it to the case where you're combining only two things in series or two things in parallel, and we'll see a grammar for it, but in a minute. But so let's see if I can get at least one triangle out of this. You see, to get a triangle, that's simply a series. This is a series network here, and here's another one, and so putting those two in parallel, I get this triangle. Okay, call this U and this V. Since Vaughn asked this question, he's just trying to get one of these books. I know.
Enough questions, and I'll do it.
Actually, the limit of 5 questions per person. Okay. Okay. All right. But in fact, let me sort of say that dash is a series parallel. Let me give a grammar for series parallel networks, because that's what's used as the input to the SP-span program. So a series parallel network, which I might call N, is either equal to a minus sign or two n's followed by the letter S, or two n's followed by the letter P. So in other words, minus minus S represents a network which means two guys in series. Minus minus P represents a network which is two guys in parallel. And then if I say minus minus S minus P, that would be this guy in parallel with one more. Okay? Or if I said minus 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 SP, that would mean that we take this one and we hook another one in parallel on top of it. Okay? So if I drew this one upside down, I would call it minus minus. Anyway, that's the formula for the triangle. And now if I want to add another triangle to that, that's easy as just another thing in series. So I have minus minus S minus P, for example, and then minus minus S minus P for this triangle, and then hook them in series. So that means put an S after that, and then okay. But now I want that to be. Let's call this U and V now, and then I want to put in parallel another guy here. So let's put a minus minus S minus P and then another P, and that would hook them together. So anyway, there's a lot of networks can be regarded as series parallel networks, and enough of them to be interesting. And so I got this program SP-span where I give a formula, and the formula another formula for the same tree, the one that I actually used, is here in the computer was this. 3 minuses SP, 3 minus SP, and 3 minus SP, and another SP to hook everything together. Now, and so what my computer replied was, it said there were 54 spanning trees, and it also told how long it took to do the calculation. Now, a lot of times when I'm instrumenting my programs now to find out how good the algorithm is, I count memory references, because of the way computers are going. The memory references are the things that are much more important than anything else, and if I just count microseconds, it means nothing next year. But MEMS are something that are going to stay the same while I continue writing my book. So the experiments that I make now, so I got algorithms and I rate them by memory references, and this particular one took 117 MEMS to get going, and then 879 more, and it found 54 spanning trees. Good, that's the right number. Okay, now if I add another thing to my command line, so I said verbose, then it tells me, what the trees are. The first spanning tree is ACFGI. Well, you have to know what ACFGI means, and the convention is that SP minus SP minus 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 SP SP. The convention is that the letters A, B, C, D are in order are used to denote the edges that we're starting with. I mean the basic edges, and then so actually, this notation allows us to build a tree. Get that, trees, where we have A and B and C, and this S joins B and C, and then actually I call that capital A. The first, all the S and P's are going to be given capital letter, and then in parallel we connect these, so that's B, and then I form D, E, F the same way, so that'll be C and D coming here, and G, H, I the same way, E, F, and then connect in series the first two, the last two, sorry, and so this is G, and then finally H. So this is this big tree represents a series parallel network. There's plenty of good seats on the edges and in the front, guys. So so ACFGI, it turns out is going to be one of these. The first one at the top of my page there, and then it tells me. Then my computer output tells me then to get the next one you add H and delete I, and then you take away G and put I back in, and so on. They keep flashing back and forth, and so these instructions are what I use to generate the pictures that were on the announcement of the page. By the way. Julian from the computer forum made me this great poster so that you can see them all in large size, and so here they are. Okay, so and in fact, what is the code? If you the code is A, B, C, D. The way I actually did it was D, E, F this way, and then G, H, I like that. You can't see. Yeah. Oh, okay. So this is the way that this is the correlation between between the trees that you see and the computer output that I had telling about the trees. Turn on. Yeah. Question?
Is the string representation guaranteed to correspond to the graph representation always 1-to-1?
There's some ambiguity if I have like minus 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 SS, because two things in series, the S operator is associative, and so you could write you could have grouped it in different ways. Minus minus S is the same as minus 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 S. But in this particular case, since I always have series alternating with parallel, I believe this, right? If this is a parallel, no, wait a minute, I'm sorry. this was a series. This was these were series. These were all parallel, and so this was series, but this was parallel. So the H and B I should have really put together, and I should have made that one glorious node here on top. I mean, actually, I would have combined it into a three. Wait, H is no. This is a series node. This is a parallel. Sorry. It's getting pretty messy. This guy, and that guy are all really, let's call it, I don't know, B. So redraw it. I have three guys in parallel at the top, and then, and then I have B and C here, and then I've got under this one I have under here. Okay, so D, E, F, G, H, I. And then now I think my program actually assigns the capital letters from the top, probably, instead of from the bottom. But the main thing is you can get a tree. And in this form, if I allow myself to have three-way branching, four-way branching, the representation is unique. But I insist now that I alternate, like if I have a parallel at the top, then everything on the second level is series, and everything on the third level is parallel again. And it's strictly alternating. And that turns out to be helpful for the speed of the algorithm. The algorithm would work if I kept binary structure and didn't suck these two parallels together. But it's actually much faster to realize this branching structure. Now, so remember, we're trying to find all spanning trees, and so what does a spanning tree look like on a series parallel graph? Well, it's pretty easy to see what a spanning tree is on the simplest series parallel graph, right? It's got one edge. That's the spanning tree. We've got to hook those together. But now, what if we have several things in series? So we got these super edges between certain vertices, and they're connected in series. What does a spanning tree look like in this way? Well, I think it's obvious that the only way we're going to get a spanning tree on this is to have a spanning tree in each of the parts that we hooked in series, because we have to be able to connect everything together. So that's the way. So recursively, if you know how to find a spanning tree for any series parallel network, or if you know how to find all spanning trees of a series parallel network, then things are hooked in series. All you have to do is find all spanning trees of each of the guys in series. No brainer. Now, how about if we hook them in parallel? This gets a little more interesting. What are the spanning trees look like? By the way, your question counts pretty good, so come see me after. So now, what do the spanning trees look like in this case? I'm going to have a connection from one to the other. Yeah, you got to.
One of them is spanning tree, but the other.
One is a spanning tree. Yeah. So I have to choose one of these four guys and put a spanning tree on it. But on the other ones, I have to have something that's a little different, and I'm going to call it a near spanning tree. A near spanning tree is something that instead of connecting everything together, it almost connects everything together in the sense that if I added one more edge between it puts everything together, everything into two parts, but not three. So if you have n vertices, you need n minus 2 edges and no cycles to make a near spanning tree. But I do need a near spanning tree on all the other. So to get a near spanning tree, then okay. So to get all the spanning trees of this network, what I have to do is run through first of all 4 possibilities, choosing the guy who's going to have the spanning tree, and then once I've made that choice, then I find all near spanning trees on the others and all spanning trees on the one that I've chosen. Okay. But now that's a new problem. I got to figure out how to find near spanning trees of of all of these guys. Okay, a near spanning tree of the simplest case is easy, no edge. A near spanning tree of a series is what? You pick one guy and find all near spanning trees of that one and all spanning trees of the other. So series is dual to parallel. All the things that you say about series and parallel, you just turn them upside down. You change near spanning to spanning, and you got it. So, because for parallel, what do the near spanning ones look like? They're near spanning on all four. So to run through all the near spanning of a parallel connection, you want to run through all near spannings of the two things. So once I got this tree structure like this, I can actually sort of say what all the spanning trees are going to look like. And here's what it is. Let me remind you, this is a parallel node at the top level here, and a series level, and then parallel and series alternating. And let's suppose I want to get, I'll put a 1 up here, which means I want a spanning tree. And then a 0 will mean that I want a near spanning tree. Now, I'm going to designate one child of each node in the tree. So let me, for example, designate the leftmost child. That's the way I get started in this process. And the idea is that the designated child always gets the same value as the parent. So A gets a value of 1. Now the other children always get the type of the parent. The type of P is 0 and the type of S is 1. So the other children are going to be 0. That's my rule for propagating values down from the top of the tree. So in order to get I have this tree, and at every node I designate one of the children, and for example I've designated all the left children, and now my rule is copy the value to your designated child, and then copy your type to your undesignated children. So P is of type 0, S is of type 1. So the 0 is going to go to the designated child here, but the type 1 is C. The 0 is going to go down here to the 0 at this node, and the type is going to go here 1. Now these are parallel nodes, so 0 is going to pass to the D, but the type is going to stay here, and then this serial is going to be like this if I did it right. The 1 is a parallel node, but the G is 1, but the H is a 0. I mean, this node is 0, and then the H gets a 0, and the I gets the type is S is a 1. So now the values at the leaves here are whether or not we include the thing in the spanning tree or not. So it's according to this, if I did it right, A, C, F, G, I is supposed to be a spanning tree, and in fact it's supposed to be the one that look at that, A, C, F, G, I. Makes me feel good. Okay, so now this is the basic idea that 0 always means make a near spanning tree. 1 always means make a spanning tree, and you can see from the rules that we gave that this is actually a faithful way. Now, in order to get all of the spanning trees, then what we have to do is just play this game with all the different designations of the children, with one exception. If a parallel node has a 0 on it, or if a serial node has a 1 on it, it doesn't matter what the designated child is. Because a parallel node with a 0 on it, all its children are 0. And a serial node with a 1 on it, all its children are 1. So in that case, it doesn't make, so what we really want to do is, if I call it an easy node in the tree. It's an easy node if the value equals the type of the node. A parallel node is 0, or the serial node is 1, that's an easy node. That means that whichever child is designated now is irrelevant. You don't have to vary the thing. So the recursive rule for getting all the spanning trees is go to, if you're an easy node, just take all of the sort of bump all of your children to go through all of their configurations. But if you're not an easy node, then for each of your children in turn, make those the designated child, and do everything, and then go to the next child and go to the next child. And all right, now I don't have time to go into further details because I have a lot of other stuff I want to talk about. But there are nice methods then. Once we've got this beautiful recursive pattern, to have all the kids doing their thing one at a time. For example, if you want to get the Cartesian product of 3D, if you want to get, if you have two children and each one knows how to generate all of its spanning trees, then you can ask say the first child to go through and do all of it, and then you make one change and then it finishes, and then you make one change to the next child, and then say the first child go through again and continue on until both but the first one, it's pretty easy to see how you can make it so that only one change is made at a time, provided I tell you one more thing, and that is if once I move my designated child from one place to the other, I'm only changing one value, and the reason is so I will rotate my body. Yeah, very good. So what I'm saying is, when I switch, suppose I had decided instead of designated this guy to designate this guy. Well, what actually happens is that only two are going to have to change, because there's a path through designated children all the way down to a leaf, which has the same value as you, and there's a path from the new guy all the way down through his designated kids down to that leaf, and so there's going to be always a zero at the bottom when I'm changing from. If I move this pointer from this branch to this branch, it's always going to mean that some below a parallel node, it's always going to mean that the one that used to be designated is going to go from 1 to 0 down at the leaf, and the other one goes from 0 to 1. And those changes only affect two things. So all of the operations that we're doing are simple changes to the final tree. Any questions on this? Yeah.
The choice of the U and V, the nodes that you start from them, depending on.
That's pretty arbitrary. That's true.
If I can have a graph with one choice, it's not series and parallel, but if you change the...
That's true. That's a good point, that sometimes the vertices that you designate... no, wait, that actually is not true, though. And I'll explain why before we go. But the actual designation that you do will happen. Well, I might as well give you the answer right now. We get it off the stack. So suppose you have a graph that's a series parallel graph, then there has to be some, it could be the base graph, but if it's not the base graph, then there has to be something that was combined at the last step, like it was two things hooked together in series. So that means there's a vertex of degree 2, a vertex that has exactly two neighbors, because that was the last, some series connection at the bottom means that there's a vertex of degree 2. So every time you have a vertex of degree 2, you just replace it. You delete that vertex and replace that by one edge. Okay, and you keep doing that until there are no vertices of degree 2. Now you look for two vertices that have multiple edges between them. That would be a parallel connection. And every time you have a multiple, you change that to a single connection, because you say that was done by a parallel step, and so then you've got a graph, and then maybe now you've got a vertex of degree 2. And so you keep on doing this until there are no multiple edges, no vertices of degree 2. So you're left with a graph has only one edge at most between any two vertices, and every vertex of degree 3 or more. And no matter which, so if you start out with a series parallel network, you would reduce it just to a single point. But otherwise, you haven't. So it doesn't. So from this point of view, it's a mistake to try to tell what the U and V are. I guess you're right that certain U and V's you're never going to do. But I guess you. Yeah. You could choose U and V's stupidly. That's true. You could like two things that are hooked in series, and then like you said, a diamond. Then you could say, oh, I wanted to get from there to there, and I can't. Yeah, but no. In general, though, I'm not really. Although people who actually do try to communicate with circuits do care what U and V are. For spanning trees, it doesn't matter. So it's a mistake to insist on your U and V. But I like to think of the U and V just because each basic unit is actually this super edge idea instead of the basic recursive structure is much nicer to think of it as the way I present it. Yeah, one more question, then I want to move on.
It seems to me that in fact you're using U and V in that whole development with spanning trees and near spanning trees because you always want near spanning trees that separate U from V.
That's exactly right. Yeah, not any old near spanning tree. It has to be a near spanning tree that breaks the connection that U and V are. That the connection from U to V is the connection. Yeah. Okay. Yeah. Come up. Well, we're going to have a tiebreaker maybe at the end. Okay. But anyway, you can play with this program and also this specification here, gory detail. If you give the if you give another thing on the command line, say extremely verbose, then then it tells you what's in the data structures and it tells you what the what the leaves are doing as you're swapping all this stuff out. And the program, if you download, is well, I did it with really large fonts here. So that you could read it today, but you usually don't get it in this size. And actually the program is quite short. The actual algorithm that generates all the spanning trees fits on a page rather nicely. But here's an example that I worked through in the notes to the program themselves. You see, here's the syntax that I gave, which is actually, and if you read through here, you see the way the program runs, and all the different error messages that you can get if you break out. And there's the theory is described in there as well. So anything that I said today don't understand, you can find the theory given here. Next, of course, there's lots of graphs in the world that aren't series parallel. In fact, if all graphs were series parallel, we'd be able to solve the traveling salesman problems and many other problems, because series parallel graphs are known to be the graphs whose tree width is 2, and a lot of people have studied algorithms that work on graphs that have bounded tree width, and if the tree width is 3, it's much better computationally than if it's 4 and so on. But series parallel are the simplest case where the tree width is only 2. So let's take now the thing that started me on this whole thing was the idea that I learned from this summer and a thesis, master's thesis actually, that came out 1997, I believe, by Malcolm Smith at the University of Victoria, and he had a really nice way to solve the spanning tree problem for an arbitrary graph. And so that's his his program, which is, and his method is illustrated by another program that you can download called Grayspan. So yeah, Malcolm Smith, 1997, University, and and so I'm again. Oh, by the way, I've instrumented the program. So if you look at the code and counting memory references, if you look at a typical place in the program here, I put in front of every statement, 00, comma. That just means I made 2 memory references in this line, and so I do this all by hand because I consider some things are known to be in registers and not really references to memory. I'm not going to trust a compiler to optimize things the right way in all cases. So I instrument it myself by hand. It doesn't take long, and his idea is again is this: you have a graph and you say find all the recursive problem that you're doing is find all spanning trees where the first one starts with a given near spanning tree. Okay. Near spanning tree. So again, I choose n-2 edges that are enough to hook the thing into 2 different components. So the first spanning, and so it's one of the things given to me is that I want that whatever my first spanning tree is, it should I know n-2 of the edges in it, only one more to find. Here's the idea. You see, if you have a graph and then there's an edge in it somewhere here, let's say from U to V, and then there's also lots of other stuff in the graph. Call this edge E. Then there are 2 kinds of spanning trees. The ones that use E and the ones that don't use E. So now let's take a look at those 2 cases. What do the spanning trees look like that use edge E? And it turns out that what we do is we've conformed the graph G dot E, which means contract this edge into a single vertex. So shrink imagine that U and V are the same and get rid of edge E. And now we got a graph with 1 less vertex and 1 less edge, and we find all of its spanning trees, and then we add E to those, and those are spanning trees of the whole. So all spanning trees of so spanning trees of G equal spanning trees of G contracted with E union the ones that don't use E, and these are the spanning trees of G minus E, this is one notation used for G minus E. So this is a recursive structure saying, if we know that each of these are smaller graphs, so we can so we do it. But we also said that all the spanning trees we were going to be given a certain near tree where we started. So what happens is that at the end, after we so we start out and we generate all spanning. We're given a near tree, so the near tree is say E1, E2 edges to n minus 2. So I contract E1, and now I find all spanning trees on G contracted with E1, and then I add E1 to those. So the first one that I actually get, it's going to turn out recursively that the E2 will be included. And I mean, you see a near spanning tree on the reduced graph we'll use edges E2 through En minus 2. So I'll find some spanning tree En minus 2 and the algorithm will find some En minus 1 that does it, and then it will go through and do its paces, and it'll end up with some random thing to F2 Fn minus 1, some other spanning tree when it's all done. So whatever it finishes with is a near spanning tree of the whole graph. And so at this point I delete that and I ask for all spanning trees of G minus E1 which the first one includes F2 through Fn minus 1. So the next thing the algorithm is going to do is then figure out some new F1 and it'll run through all of those. That's the idea of the recursion. And there's a really cute way to put these all in memory so that you, instead of using a stack for the recursion, you actually have a linear list where all the things you're supposed to use are sitting there on a list with a little hole in the middle of it. And I don't have time to go through the details, but I can show you how the program works when you play with it. It runs exactly the same as I got another program to play with that's called SP Graph, and what you do, so if I run here, I kept forgetting how to use it. So I run SP Graph program and I give a formula. If I happen to have a simple graph, which is a series parallel graph, I can give the formula and it'll create a file that represents that graph in the format used by Stanford GraphBase, a whole bunch of programs that I have for dealing with graphs and other combinatorial algorithms, and so it makes the GraphBase graph demo.gb, and then I run my program Grayspan on demo.gb, and it says, oh, okay, it found 54 spanning trees, 6,000 and some mems. As you would expect, since this Grayspan program is more general, it's not going to work as efficiently on a series parallel graph. The series parallel graph it only took less than 1,000 altogether, but so it took about 6 times as long. But it's a much more general program, and it did find the 54 spanning trees. And again, we can ask for it doesn't matter what you put on the command line, as long as you have another argument on the command line, like I put a plus sign here that gives you the verbose information and told how long it took to get going, and then and it also tells you the numbers that it has assigned to all the edges of the graph. And so here's your first spanning tree and the second one, and again, if you ask for after the 54, then if you ask for extra verbose, then you get a lot of gory details about exactly how it goes about it. And the program is actually much shorter than the program for the series parallel graph case. This program has to prepare the graph, and it has a fairly simple, but it has lots and lots of printouts just to do this verbose printing. So you describe the method here that I just described to you, and when you actually get to the code, it's quite simple. But the only complication is that that we're shrinking the graph, and then we have to backtrack and unshrink it again. I left out one little complication. We don't want to look at if taking out E1 disconnects the graph, then I don't want to do that step, because it's called a bridge. I have to have a connected graph. So I have to make a test after I finished looking at this one. I have to test whether I'm done at all, because so I make it so I delete this edge, and then I make sure there's still a way to get from U to V. If not, then I just don't, then I don't have to worry about this guy at all. It's not connected. Okay, so I have to do that. So that's the point here. It says, I shrink it, but then I have to unshrink. And if it's not a bridge, delete it, and remember the edge that you've changed. And I have go-to statements in this program. Don't be shocked. The beauty is actually that the unshrinking method, we keep the representation of the graph as a doubly linked list, and this means that undoing is extremely simple. A couple of years ago, I gave a lecture. One of my lectures was about what I call dancing links, which is a technique for undoing that requires only very small changes to a data structure. So we can shrink the graph by removing edges and changing a couple of links, and we can unshrink the graph without much extra work. And there's a much better way to do lots of combinatorial programs that require backtracking, undoing. So the dancing links method, which I presented in connection with a completely different problem, turns out works in many different methods. And then bridge detection is just we're just doing a breadth first search. So the whole code turns out to be quite short. When I put it into Art of Computer Programming, it's going to be an algorithm only about 9 or 10 steps long. So that's the experience that we have with that, and I can show you the one other program that I have. Oh, yeah, there's lots and lots of output though. It does all this work. No wonder it took 6,000 minutes. Okay, going. But it has to. Everything you do, you have to be able to undo, and you have to check for bridges. Okay, so, but this was the extra verbose output. Telling it was very handy when I was debugging. But the program was so simple it really didn't take much time to debug since there was almost nothing to get wrong. However, then I wrote a program called Grayspan, and this is the one that is guaranteed to be efficient. And here's the idea. If we look at the program Grayspan, which I can read it to you. This program combines the idea of a Grayspan and SP-span, resulting in a glorious routine that generates all spanning trees, changing only one edge at a time with guaranteed efficiency, in the sense that the total running time is a constant times m plus n plus t if there are m edges, n vertices, and t spanning trees. That's as good as you could expect to have if you're going to generate all the spanning trees. You can count all the spanning trees by evaluating a determinant, but this is saying we want to generate them. And now this program, again, has the same conventions as the other programs, but it uses the idea I mentioned a while ago, that first if you've got a graph and it has several edges between the same two vertices, these are called parallel edges, so we say, okay, let's combine those two into one. If we have a vertex that has degree 2, one vertex only has 2 neighbors, we can eliminate that vertex and consider the 2 edges that used to join that vertex to be a super edge between them again. In fact, the word super edge turned out to be fairly long, so I decided instead to call it a bond, and that turned out to be a nice 4-letter word. It worked, So let's say that a bond is something that happens in this recursive process. I start out with a graph, and I consider that its edges are bonds, and then if I have 2 parallel bonds, I combine them into one bond. If I have 2 bonds in series, I combine them into one bond until finally I have a graph left where it's either a trivial graph, only one point, or it's got at least 3 bonds coming into every vertex. Okay, and now in this graph I can use Smith's algorithm. the idea is that suppose I run through and find all spanning trees of the graph with the bonds. With me? So I have a graph. Let's suppose that suppose, for example, that my graph has reduced to the smallest non-trivial graph that doesn't has 4 vertices and they're all connected to each other. So so this complete graph on 4 things is the simplest way to have every vertex of degree 3 or more, and so suppose that my graph, but each of these are not really edges, but they're bonds. That means that they could be any series parallel network between the 2 edges. Okay. Now, suppose then that I find one spanning tree of this guy, maybe this one. Then what that really means is I want to find all. I want to find all spanning trees of these series parallel networks and all near spanning trees of the ones that I haven't used. So in other words, I apply Malcolm Smith's algorithm to this big guy, and for every spanning tree it outputs, I run through all the spanning trees of the bonds and all that are included, and all the near spanning trees of all the bonds that aren't included. And I can do that just changing one branch at a time. Not only that, but as you look at Smith's algorithm, you delete a bond, and then all of a sudden you've got vertices of degree 2, and the graph contracts again. So all the time you're applying this idea. When you reduce the graph by shrinking together, by shrinking one of the edges and bringing the points together, or by deleting one of the edges, again you have a chance to build further bonds. This leads to a really interesting data structure and doing and undoing situation, where the series parallel graphs that are coming up keep changing all the time, and it turned out to be one of the most interesting programs I ever, or certainly the most interesting one I did this summer. And here it's a fairly chunky piece of code. I mean, well, 50 parts to the program. Each part is, well, in fact, let me talk a little bit about debugging it, because I had, here's the data structure. Wait a minute, where's the data structure for the bond? Let's see. Okay, here's the data structure. So a bond, you have a type and a value that we had in our series parallel algorithm. We had the left child, the left sibling in a family, a right sibling, the designated child, the final designated child. As we're going around the circle, we have then things I needed for to control my algorithm that goes through in gray code order. And I have left and right in a list that's also implemented in the gray code order, up and down. And then I have, in order to undo, there wasn't enough information in the data structure unless I introduced 2 more fields, and 2 additional history values. So it's a huge data structure with a lot of redundancy. So when I have to debug it, I find it very important to have sanity check routines. So sanity check, and then I put flags in there to say what kind of sanity I want to check at a particular time. As I'm debugging, I got to find, because the algorithm is going to run in a long time, and it's going to really, if a program runs for 10 minutes and then all of a sudden it hangs, you want to know when the data structure first got out of order instead of a few minutes after after you had a missing link and it started to screw up. So so then I have all these checks on the redundancy going in. That makes the program longer for sure. But when you look at the at what happens to do when you're shrinking nodes, and let's see, where are we here? Make series, make parallel. There's lots and lots of data structure manipulations, doing, undoing, deleting, undeleting. And so what happened was I tried this algorithm out on the complete graph, first with with 4 nodes, the simple case where there's 4 vertices and everything checked up, and to make sure first that would work. And then I tried it on the complete graph of 5 nodes. Now, while you're working on a complete graph of 5 nodes, it deletes edges, and so you get every other graph somehow in the process. And so any bugs, I was just testing it on complete graph instead of on other graphs because as you start with a complete graph and you delete edges, you run into lots and lots of other graphs anyway. And so it worked on after then another 5 bugs and it worked on the complete graph of 6 vertices. And then I tried it on the complete graph of 7 vertices. The number of spanning trees is going up and up and up. It's the end of the n minus 2, but still not too bad. And so, sure enough, a few more bugs showed up in 7 vertices. But then I did 8, it worked fine. And I did 9, it worked fine. And I did 10, again it crashed. And I found 4 more bugs. But now I'm sure it's correct, although I haven't really gone through it. But incidentally, the running time for generating in the complete graph of 10 things, the number of MEMS was 1.9 billion only. So it wouldn't have been bad to go to go up to the next case, although that's it's going from 10 to the 8th spanning trees to 11 to the 9th. But it's still I could go up a little further, but I'm convinced that it's working now. But you might find it not if you download it from the web and try it. But these sanity check routines were extremely important because I could have, every time I did anything to the graph, I would then do a sanity check and I would find out, oh yeah, that's where the bug is, because there's so many cases that arise in these changes to a data structure that has lots and lots of redundancy. And I believe that whenever you're running a program that has such data structures, that's a very valuable debugging aid. And so it didn't take really too long, although I said here, programming task still was tedious and error prone. Okay, so there's comments as well. Now, the other thing I wanted to tell you is why I can guarantee that this program is efficient. Because if you look at the recursive method and you see that I really in order to change what I need to change to get from one thing to another, I'm not allowed to do much calculation if I'm only allowed a constant amount of operation per output, amortized over the whole thing. And the reason is that I was able to prove that there are lots and lots of spanning trees if the graph is reduced. And so here's a result that I want to explain to you the next few minutes. It's a theorem that I asked to the people who ought to know if it had been proved before, and it seems to be new. It says if G is any connected multigraph without loops, you have to have all these hypotheses. So connected means that that does have at least one spanning tree. Multigraph means that you're allowed to have parallel edges between two vertices, but loops means you can't have any edges from a vertex to itself. Then it has the total number of spanning trees is traditionally called kappa of G, the number of spanning trees. So the number of spanning trees it has is greater than the product D1 minus 1, D2 minus 1 to Dn minus 1 spanning trees, where dj is the valence or the degree of vertex j. So the number of neighbors of the vertex, including multiple neighbors if there's a multiple. So this is the theorem. And in particular, if we have a graph that doesn't reduce anymore, all these d's are at least 3. There's no vertex of degree 2 or 1. Okay, a vertex of degree 1 is an endpoint. That you know, really trivial. So that means then that I have at least 2 to the n, you know, the square root of 2 to the n spanning trees. This grows exponentially with n. That gives me plenty of time to do the other calculations that I need to figure out the series parallel working on the bonds. And that's the reason. So it's because of this theorem that I can guarantee the efficiency of that super method. You can show that without the super method, it's kind of embarrassing. You start with a cycle and you try to find all of the spanning trees of a cycle, and there's only n of them, but it takes you n squared time to do this. So you need a theorem like this in order to do it. Okay, now the proof is I'll just sketch it for you, and I suppose you could reduce this proof to a proof using determinants if you were really good at matrix theory, and so those of you who want to check it, you could. But anyway, the case 1 is that G is connected. It is let's suppose U and V are vertices that are connected by K edges to each other, and then there's other vertices, other edges going out to other to the rest of the graph. Let's say A on this side and B on this side, and I take G is my original graph, and G2, G1 is G with U and V identified, and I would collapse all these, shrink all K of these edges together into a point, and G2 is G with those K edges removed. So then the number of spanning trees of G is equal to K times the number of spanning trees of G1 plus the number of spanning trees of G2. That's easy to see. You have to choose one of these edges and do it on the others, or you can do this way. Okay, so now I use induction, and I want to prove it. So you know, these are smaller graphs, and they're and so case 1 is that G2 is connected. Then I can, if G2 isn't connected, then I couldn't use the induction hypothesis because I need to be connected multigraph. So in that case, then what am I saying? Well, cap of G1 is greater than or equal to square root of A plus B minus 1 times alpha, and cap of G2 is greater than or equal to A minus 1, B minus 1 alpha, where alpha represents product of the degrees of all the other vertices besides U and V. You see what's happening is G1. I've combined these vertices together, so the new thing has A plus B neighbors, and so the degree minus 1 in my formula is A plus B minus 1. Alpha represents the product over all the other vertices. Well, in G2, I've deleted these two guys, and so now I have A. So now U has degree A and V has degree B, and so I have this one. So all I have to show is so I just have to prove then that K times square root of A plus B plus 1 plus the square root of A minus 1 B minus 1 is greater than a plus b, greater or equal to a plus b minus 1 times a plus k minus 1 and b plus k minus 1. Yeah, I just have to prove this if ab is greater than 0. So if a and b are both greater than or equal 1, then you just have to prove this, and it's simple calculus to do it. So the second case is there are no such u and v where with G2 connected. In other words, it's always a bridge whenever you have, whenever all the parallel edges are bridges here. Okay, so every multiple edge of G is a bridge, and that means it's a tree, a free tree, except for parallel edges. And if there's a vertex of degree 1, the result is obvious, because if any of the degrees is 1, you get 0 here, and the statement is obvious. And if you don't have a vertex of degree 1, then you've got some endpoint though in every tree. So there's an endpoint where it's not connected to anything except v, and there's k vertices here. Okay, and so the degree of u is k. The degree of v is k plus 1 plus x. Because it's obvious if there's there's some other guys here. Okay, so then there's a simple case analysis. Depending on what x is. If x is positive, it's easy. If x is 0, it's easy. And so that the proof. I'm near the end of time. So again, we just have to verify a few. Like in the case where I'm sorry, if u and v were here, my theorem would be that k is greater than the square root of k minus 1, which happens to be a tight inequality. So if there weren't anything, on the other side of v, what?
Oh, sorry.
If there wasn't anything on the side of v, that my theorem would certainly be true. So then I put here, and so I have to consider this case, but it does work out very nicely. And so that's the theorem says that there's lots and lots of spanning trees if you don't have the collapsing that that's present. So then it's easy to make a proof that the total running time is linear, as we said. Well, so does it really save a lot of time compared to the simple algorithm that has a bad that doesn't do too well on cycles? And the answer was, on the complete graph, the simple algorithm took 3.8 billion mems, and the complicated algorithm took 1.9 billion. So a factor of 2 for all my programming. But I learned a lot while I was programming. And it's always nice to have a theoretical guarantee. Makes it looks like you've done your homework. More questions?
Can you find the upper bound on the number of spanning trees?
Excuse me?
Can you find the upper bound on the spanning trees?
Upper bound, yeah. There are some upper bound. Well, see, this is actually there are upper bounds, but they're like, we take out the square root here. I mean, I can't remember what it is. I'll have it in my book, but there is a upper bound based on degrees. But certainly, for example, the product of the degrees is an upper bound, but that's maybe too trivial. But yeah, but I don't remember the. Yeah, not a bad question though. Yeah, it's pretty hard for me to keep score on the best questions in this. Yeah.
So G1 and G2 correspond to the units of your two operations. So the first one is the unit of S, and the second one is the unit of P. The middle graph is the unit. it's identified. You've got the not by your definition of graph, extended to include single pointers of empty disconnected is another one, and they're the respective units of S and P.
Are you saying in a special case of trees with multiple edges?
Yeah.
And this bound seems to be tight, really tight, only in the case of a path that has like it seems to be where you have something like this, lots and lots of edges and then one, and then lots and lots of edges and then one. Lots and lots of edges, and you let these numbers go to infinity, then it shows that my theorem is the best possible in the sense that I can't put a 1 plus epsilon here for any positive epsilon.
Well, you and me identified as just a node. And if you take all the k edges out, then it's 2 nodes that are disconnected.
If I multiply by all the k's, then some of the d's, yeah, that's a good idea to think about that.
So in other words, it boils down to reducing
leave out the word multigraph.
Mm-hmm.
The reason I wanted it to be multigraph, though, is because of the induction. You see, because as soon as you collapse these two together, all of a sudden you're getting parallel edges, because some of these things U was connected to was already, and V was already connected to them too. So those become parallel edges, and you can't use the induction easily. Yes?
Can we generate spanning trees using node deletion rather than edge deletion?
Spanning trees using what?
Node deletion, vertex deletion. So
vertex. See, a spanning tree is really an edge property. It seems.
One node and find all the spanning trees and add
delete.
edges.
Yeah, that's delete one node and everything touching it, and then yeah. Okay. Well, that's a good research problem. Maybe you'll come up with a faster algorithm. Yeah. But at the moment, this is what I know.
How long did it take you to write this super program?
The code? Well, let me take. Actually, what I spent 4 days trying to do the following, which is totally academic. The SP span program for series parallel. Since it had this beautiful algebra and all this duality and things going in here, I said, okay, now I'm going to go further, and I'm going to write a loopless algorithm. A loopless algorithm means that not only is the total running time linear in the amount of output, but I don't allow myself to ever do an unbounded amount of computation. I mean, the running time of this program is the total running time is proportional to the number of spanning trees, but between the 10th and 11th spanning tree, it might take a while, and then it'll start generating lots and lots of spanning trees again fast. So the amortized running time is linear in thing. But what if you say that no, you're not? You put an absolute bound on the amount of time between spanning trees. Spanning trees have to come out at a constant pulse rate, and I was almost there to having a loopless algorithm for the series parallel spanning trees, and then it would break down, and so then I had to. Then another 2 hours would go by, and I thought of another way, and then that would fail too, and for 3-4 days I finally decided, okay, I've used up my budget on this. If I don't get it now, I mean, I tried all kinds of things about instead of changing one of the things was the problem is, you see, that we have easy nodes and not easy nodes in that algorithm. The easy ones, remember, were the ones that the type was equal to the value. That meant that a series node of value 1 or a parallel node of value 0 was easy. And when you make the change to designate another child, all of your easy descendants changed. They're no longer easy, and all the uneasy ones have become easy. So you're complementing the easy uneasy thing, and that was and I had to be able to do that in my data structure sort of in a lazy way instead of simultaneously. And so I kept going around and around and around until finally I after 4 days I solved that problem and I got it out of my system. But that was the longest part. The rest of it was I would say about I mean, certainly the first program was a day, and this gray SP span, I think, was 3 days, including 2 days of debugging. I mean, because the debugging was the major thing. And I didn't have the phone ringing either. I'm retired now, so I don't have to answer email. So I can work a lot faster than most of you guys.
You don't have to answer email even if you're not retired.
Well, I'm retired from email is what I meant. Yeah. But the code, I find that I'm writing this code and I'm putting the English explanations in the code, and that actually saves me time. I find if I'm trying to write the program and explaining it as I go, assuming that somebody's going to read it, even though it's usually just for my own benefit to read. When I wrote the program, I didn't know that I was going to be putting it on the web. I write it. I try to explain it to myself as I'm writing it, and I find that does speed up the total amount of time because I get my thoughts in order much better that way. Somebody caught the little joke I had in there about bond. Well, also there was another one. If you compare the programs, one of them says this is the current edge of interest, and when you go to the corresponding comment in this one, it's the current interest-bearing bond. So I have fun while I'm doing this too. Yeah. Any other questions? Okay. Well, now I have to choose the people who ask the best questions, I guess, and I don't know how to do the damn thing. Okay, but I guess the ones who asked the first two, you two guys are in on it, and I guess I think you two also. I mean, Vaughn already has the book; he doesn't need it, right? So yeah. Okay, so thanks very much.